we're looking at a special class of differential equations, specifically of the type we started with, where we have a function of x and y times the derivative, plus, again, maybe a function of either x or y, and that equals 0. So exactly where we were before. Note that algebraically, you can always rewrite this so you can solve for dy dx, so you can solve for the derivative. So you could always rewrite, and that's what this looks like here, which means that you can always write this this sort of differential equation as the derivative or the slope equals some function of x and y. What this means is that wherever you're at on the coordinate plane, you can always substitute the point you're at, x and y, into this formula, whatever it is, and it'll tell you exactly what the derivative is at that point. Moreover, what that means is that when you plug in the coordinates you're at, you can always find the slope of the tangent line of whatever the solution happens to be. So that means that you could think of the coordinate plane as what's called a field where you can find all the slopes, or hence a slope field. So specifically, the definition of a slope field is the set of all tangents. The set of all tangents at all points x, y of a given differential equation. So this means that we could think of a grid. For every point that's in the coordinate plane, we could take that xy pair, plug it in for this function that we've created in terms of x and y, and then I will spin a number. That number is the slope of a line that's tangent to the solution of this differential equation. So we can get a plane that's filled with slopes. Now, obviously, you can't do this for every single real number x and y. You just have a grid of just lots of little tiny lines that you can't read anything. So often we'll create one that's like, say, for all whole numbers or all integers, like in this in our first example down here. So often you won't do it for every single possible point. You'll do it for a collection of points, like regularly spaced along the way. Also, in that slope field, we can identify things called isoclines. Is a collection of all points in a slope field. This is all points in a slope field with the same slopes. With the same slopes. These often do not, and as a rule, will not follow the slopes in the slope field. But what they will do is that we're gonna find every point in the slope field that has the same value. So often, like a table of what the slopes will be most useful for identifying isoclines, and we'll go through an example in just a minute of how you might come up with like a rule for drawing an isocline if you don't have access to a table or haven't made one yet. Note that computers are the best at making these. In fact, like a spreadsheet could be a really efficient way to construct a slope field in practice. On any exam, whether that would have been the IB exam or the AP exam, you won't have access to that as a rule, and often you're not going to make by hand very complex slope fields, but you will on occasion be asked to create one. So it'll be we'll do an example here of a sort of slope field that you might encounter will be useful, and we'll make one and try to going to do this step by step here. So let's consider this differential equation. Dy dx equals x times y. So the again, this differential equation tells me that the slope of whatever the solutions look like, the slope at any point of this is just the x, wherever is just wherever you're at in the coordinate grid, just the x coordinate times the y coordinate. What we're gonna try to analyze this a little bit further. We're gonna identify a solution to this, which is step A, and then we'll go from there, construct some a slope field, and so on and so forth. Okay, so just like in the previous example, we're going to verify that we've got a proposed solution. I want to verify that this actually solves this differential equation. So again, we want to show that dy dx actually solve, or that this function of y in terms of x actually solves this differential equation. So again, I know what y is some constant times e to this time x squared over 2. And just like before, I can take the derivative of both sides, and I'll have a dy dx on one side. And let's see, if I take the derivative of the right side here with respect to x, let's see, this will be using the chain rule, I need to find the derivative of the top, which will be 2x over 2, or just x, times this constant that was in front c, and again, the derivative e of the x is just e of the x. Note that y is equal to c times e to the x squared over 2, which, what do you know, we have right here. So note that this is equal to x times y, which is exactly what we wanted. So we've shown that this, in fact, is a general solution for some constant to be determined. A slope field using integer grid points on the intervals from 0 to 4. Meaning I'm not going to bother with any decimal or fraction values for my field here. Oh boy, this is bad. No, we'll make it work. It's just a rough sketch as it is. So there's y from 0 to 1, 2, 4. Okay, so what are some things I know about this differential equation? I know that the slope at any point along here, at any point on this grid, is just x times y. So I know a bunch of slopes right off the bat. I know that, and I'm going to draw them in. How about draw them in red? So I know that any of the values that are on the axes are going to be 0 times any value, which is just 0. And a line with slope 0 is horizontal. So I'm going to draw little horizontal lines to represent the slopes at each of these points. And again, along the y-axis, there are horizontal lines. Okay. What are some other slopes I know? Well, what I'm going to do now is, like, at each of these integer points, I think of, if this was graph paper, I think at each intersection, I'm going to draw like a small line that has slope of whatever the value is. So, like, for example, at 1, 1, the slope at the point x is 1, y is 1 is 1. And I know a line with slope 1, oops, does not look like that at all. But it does look something hopefully like this. Fine. Line of slope 1, ideally it would have been like at a 45-degree angle, but I'm still learning here. And I know at this point, 1, 2, the slope at 2. So ideally, I would try to draw a line that's like the slope is twice as big, or rise over run 2 over 1. And I also know that at 1, 2 and at 2, 1 have the same slope. So I know that ideally, these two lines, oh boy, these two lines would have the same slope. Okay, I've used Desmos here to, in a program you can, or a file you can find on Desmos if you would like. But this is just going to be a little bit way easier for me to show you what the slope field might look like. in this case, without my sloppy computer handwriting. Note that the function here is the derivative is x times y, and at every integer coordinate I have set up, this is much larger than you would need to for this particular example. We'd only need to go in this little window here 4 to 4. But note that, I'll try to zoom in, that at 0, 0 and along each axis, the slope is horizontal. And each axis, the slope is horizontal. And at 1, 1, the slope is 1, down 2, 3, and getting steeper. Same slopes here because it's 2 times 1 and 1 times 2 are the same. 2 times 2 is 4. Note this should be the same as 4 times 1 and 4 times 1. Those are all 3 slopes are the same, and so on. And they get, since x times y gets progressively bigger as both x and y increase, then the slopes get progressively steeper as you move on. And it can be very difficult to draw like increasingly steeper and steeper slopes by hand. So when you do it on your paper, just do the best you can. And clearly showing that as you move further to the right and further up, that the values of the slope field are continuing to become steeper. In place of my terrible hand-drawn slope field, I've inserted just the relevant part of the Desmos image slope field, so we can attempt to do the remainder of this problem. Okay, so part C. Let's sketch the particular solution curve through the point 2, 1. Without an actual equation just yet, we can still sketch solutions to this. What I'm going to do is I'm going to find the point 2, 1 on my curve, which is right here. And then to sketch a solution, I'm going to draw a curve that that more or less follows these tangent lines. So I know that it's locally tangent right here. So this curve somehow is definitely a slope of like 2 right here. Let's see if I can actually draw this somewhat correctly. It has a slope of about 2 locally here. And then as I keep going to the right, it gets steeper and steeper and steeper, and my line is very wavy. Hopefully, when you're not using a computer, yours will be less wavy. Note that if I were to try to follow what I imagine the slopes would be coming down in this way, note that as I get down here, both x and y are decreasing, so the slopes are decreasing. So it's definitely becoming more flat as I work my way to the right here, and it's got to have to decrease because by the time I get to the origin, it has a 0 slope because the x coordinate will be 0. So, while not perfect, this is a proposed solution. Again, as you encounter more on your solution, as you encounter more of the when you encounter a line at an intersection, a slope, that your curve should be tangent to that line at that point as well. I'd like to, okay, let's verify algebraically that this curve I sketched is in fact this particular curve. What this question is saying is that I want to verify that at 2, 1, that this is the actual solution to this. So let's see, maybe I'll do this over here. So part D. So I want to show that when I'm at the point 2, 1, that the constant is 1 over e squared. So I'll take let's just take my my solution, and I'm going to substitute in x is 2, y is 1, and see what we come up with. And I think it's going to be pretty straightforward. So y is, because y equals c times e squared, e to the x squared over 2. So let's see, 1y is 1. We have c times e to the 2 squared over 2. Which says that 1 is equal to c times e to the 2 squared over 2. 2 squared is 4. 4 divided by 2 is 2. And when you know, divide both sides by e squared, c is equal to 1 over e squared. Or better yet, y equals 1 over e squared times e to the x squared over 2. Okay, lastly, I want to take we need to take this curve and we need to draw isoclines that correspond to each of these values of k. Remember, an isocline is a point on the in the slope field, all the points in the slope field that have the same slope. So what this is telling me is that I want to find for each of these three values, I want to find all the coordinates, or be able to describe all the coordinates where dy dx is equal to each of these k values for 1, 3, 6. We can find maybe the first one, and then it'll clue us in how we can print the rest. So this is saying I want to set dy dx equal to, say, for the first isocline, I want to set equal to 1. So I want dy dx equals 1. But note this is also equal to x times y. Meaning if I could rearrange this equation to be a function of y, then I would know. Then I could use that to graph and find all the coordinates here. So maybe better yet, I think y. This is telling me that y is equal to 1 over x. For this relationship, I'll have all the points where the derivative is exactly equal to 1. And note, we already know at least we can find a few by hand on my graph here. I'm going to graph this first isocline where k equals 1 in here. So I know one point where the derivative is 1. That's right here at 1, 1. But also I know some other points. And this will help me find any other combination. A y value and its reciprocal. So how about at the point x is half, but y is 2. There's another point on my isocline. And my computer keeps erasing these points. How about when x is 2, y is 1? Oh, this is annoying. 1/2, 2. 1, 1. 2, 1/2. We can find some others as well. How about like 1/3? How about 3, 1/3? How about 1/3, 3? And what we get, unsurprisingly, is this part of a hyperbola, which, oh boy, I am so. Well, actually, the end of this wasn't so bad. So maybe I'll try this one more time. I got good by the end. How about not much better. Well, this part's way better than for up here, but this is the isocline corresponding with k equals 1. I could do a similar isocline when k is 3. Same analysis tells me that I want 3 equals xy, or better yet, y equals 3 over x. Which is every place where again, this is saying I want this isocline is every value in the slope field, every point in the slope field whose slope is 3. And again, I know a few of those. There's one here, there's one at 3, 1, and there's a bunch of others, but they form a hyperbola again that looks something like this. And again, lastly, for k equals 6, there'll be one where the isoclines are all 6. There aren't that many points. Oh, there are 2 points. 2 times 3 and 3 times 2. And again, this is an isocline that corresponds with k equals 6 because these are all of the points like 2, 3, and 3, 2, whose slope is 6. And again, that has as we saw, corresponds to graphing this equation 6 over x.